Hey there, here's another screencast. This one I'm calling t-distribution, small samples. In this screencast, I'll talk about what we do if we're trying to create a confidence interval for the sample mean, but our sample size is too small. So we can't use the central limit theorem. So let's start. Say that we've got some measurement that's we're estimating. And let's say its measurements follow a random variable we'll call x. And let's say x has mean mu and standard deviation sigma. And often we don't know what they are, but we'll just say that these represent them. Now, suppose we're trying to estimate the mean of this distribution. The central limit theorem which I'll abbreviate CLT going forward, says the sample mean will be approximately normal. If the sample size is large. So say n is bigger than 30. This is what we mean by large. Moreover, the central limit theorem says the sample mean will be approximately normally distributed with mean mu and standard deviation sigma over the square root of the sample size. So just note that the mean of the new sample mean is the same as the mean of the previous distribution, the distribution that we're studying. And the standard deviation of the sample mean can be derived from the standard deviation of the original. In practice, of course, we don't know what the original distribution's mean is. We don't know what its standard deviation is, and we guess these by samples, or we approximate them by samples. But let me proceed. In such a situation where our sample size is big, we assert that the standard deviation, the sample standard deviation, is going to be approximately equal to the true standard deviation. And it's going to be very close. So the error we're going to assume is 0. So in practice, we say the sample mean is distributed normally with mean mu and standard deviation s over the square root of the sample size. This is in practice how we do it. And we use this to calculate confidence intervals, right? To calculate a confidence interval, we take a particular sample mean and we say plus or minus z alpha over 2 times the sample standard deviation over the square root of n. This is what we do. And we can do this because the sample mean is distributed normally. Or, and I saw this, or I gave this to you, or told you about this in another screencast and in class, you can use R to calculate these endpoints directly. And I'm putting a blank here, and in this blank, you either put alpha over 2 or 1 minus alpha over 2. 1 gives one endpoint, the first gives the left endpoint, the second gives the right endpoint of your confidence interval. So now what I want to address today in this screencast is what if n is less than 30? There's all kinds of stuff you can't do. The central limit theorem does not apply. because the central limit theorem does not apply, x bar sample mean is not necessarily normal. When the sample size was big and we could use the central limit theorem, with the central limit theorem, we could calculate this quantity, the sample mean minus the mean divided by the standard deviation of the sample mean. These were what were called the z-scores of our sample mean, and these were distributed normally. Actually, they were distributed like the standard normal distribution. That's when the central limit theorem could be applied. Now, in our situation, when n is not large, and we're looking at these numbers are not normal. And I'm going to tell you what distribution they follow, but these are not normal. And it's also important to note that the sample standard deviation is not necessarily going to be close to the standard deviation. And the sample standard deviation is not necessarily approximately equal to the standard deviation. So, consequently, there's a new distribution that we'll use. This thing here follows what's called the student's t-distribution. And that's what I want to talk to you about today. So the student's t-distribution is very similar to the standard normal distribution in the following ways. Okay. It's symmetric about 0. In fact, it's symmetric about its mean, and its mean is 0. And it has a similar humped shape, similar single hump shape. Right? When I sketch the student t-distribution and when I sketch the normal distribution, they're going to look the same. The differences are very, very subtle. So what are some of the differences? The student t has more area in the tail. So if we were looking in the tail and we had the graph of the normal, the graph of the student t would be a little higher. There's more area out there in the tails. What else to say that there's different? There's a different t-distribution for each sample size. So some books like to use a subscript to distinguish between them, and I'll explain why in a second. I'm going to put an n-1 there for sample size n. And as t grows, no, not as t grows, as n grows, t sub n-1 becomes closer to the normal distribution. And in fact, for all intents and purposes, we say t of 30 is approximately equal to the z distribution. So when you've got a sample size of 31 or larger, that's when we can invoke the central limit theorem, and that's when we start using the normal distribution. But when our sample size is smaller than 30, or 30 or smaller, then we use these t-distributions. All right, so what about this? What about this n? Oh, another thing to say is with the normal distribution, we have normal distributions with mean, mu, and standard deviation sigma, where mu is not equal to 0. Well, we don't have an analog. In the t-distributions. All our t-distributions, we're going to think of them as centered at the mean mu. All right, so for each n value, there's going to be a single standard t-distribution. So the analog is like this. The t-distributions should be, you should think they're analog to the standard normal distribution, a different one for every n. And I'll tell you, well, what that means then is if we're going back here and I said that there were two ways to calculate a confidence interval, and one we could just invoke this qnorm command directly for the normal distribution centered at mu, or centered at x bar. Well, for t distributions for confidence intervals of small sample size, we sort of are forced to work in this context. That's why it's good to know how to do this for the large sample size sample means. I guess the last thing I'll say about the t-distribution is the textbook has some pics on page 345. So you can see how the distributions change as n changes. It'll give you a good idea of what's going on there. So one thing I want to tell you that's important to know about distributions is the sample size. So if you say your sample has size n, this determines which t-distribution to use. Okay, we're going to use the n-1 t-distribution. And this n-1 here, this is called the degrees of freedom. Of the distribution. Okay, and you can maybe the number of degrees of freedom. And the way I like to write it down is like df for degrees of freedom. And it's always your sample size minus 1. And that's why that subscript goes on the t-distributions, the n-1 subscript. That stands for the number of degrees of freedom. So if you know your degrees of freedom and your alpha level for your confidence, then we will have this number t sub n-1 comma alpha, or t sub n-1 comma alpha over 2. Right? These are our percentiles that we use when we calculate confidence intervals for sample means when we use small sample size. So we're replacing that z value with a t value, and then there's an additional subscript in there. So I'll work an example so you see how this works. All right, so how would I summarize this? I guess I'd summarize this by saying the confidence interval now is going to look like x bar plus or minus t sub n minus 1 for the degrees of freedom, your alpha over 2, and then times our standard deviation. So everything we learned about the confidence intervals for large samples to estimate a sample mean still works. The only thing you switch out is a new way to calculate this multiplier. In summary, if your sample is less than 30, then, I guess I didn't mention this before, we also need to know that our original distribution is normal with some mean and standard deviation. Doesn't matter what those are, but we do want to know that the original distribution is normal. Because the t-distribution its distribution is very symmetric and very normal-like. So that's why we need this. So we tend to look for symmetry, no outliers. So this is what we look for in our sample data. We want symmetry and we want no outliers. And box plots are a way to do this. There's a thing called a normal plot the book talks about. But when you use a box plot, you can see whether or not the data looks symmetric by looking at the box plot, see if the whiskers are symmetric, and see if the mean is right in the middle of that box. And then box plots also give you a way to see if there are outliers, a concrete way to see if there's outliers. Continuing our summary, confidence intervals use the t-distribution with n minus 1 degrees of freedom. And then finally, the confident intervals have the form of the sample mean plus or minus this t percentile for alpha over 2 times the standard deviation of our sample mean. Okay, so let's use this and do an example. All right, so we're back at our manufacturer of widgets. A new quality control engineer takes a sample of size 20 and calculates its average weight to be 15.7 grams and its standard deviation to be 1.35 grams. If we know that the widget weights are normally distributed and don't have any outliers, let's calculate a 90% confidence interval for the expected weight of a widget. So first we'll figure out what's the alpha value that goes along with 90. Well, 90 equals 100 times 1 minus alpha. So divide both sides by 100, and we get 0.9 equals 1 minus alpha. So alpha is clearly 0.1. And then we'll use alpha over 2. That's 0.05. So our confidence interval has endpoints that are given by x bar is plus or minus. So we have our t-distribution that we're going to use, and it's a t-distribution with 19 degrees of freedom because our sample size was 20, and the alpha over 2 value is 0.05. And then the standard deviation we're going to use is our sample standard deviation divided by the square root of our sample size. All right, so that's how we're going to compute the endpoints of our confidence interval. All right, so x bar is 15.7. So the command in R for calculating this, now we can look at the textbook and use its table, and I'll do that in a second. But the command for doing this is simply Q for quartile, T for t-distribution. So that's the command, and it's got two arguments. The first argument is the probability or the percentile level that you want, and then the second argument is the degrees of freedom. Right. So let's throw all that into R, and we get negative 1.729133 for the t-value. And then for our standard deviation, we get 0.3018692. Sorry for losing space here. Multiplying those things out, we get negative 0.5219719. So our confidence interval is 15.7 minus that number there is 15.17803, and then plus that number 16.22197. Or if we want to round, we could round to the nearest second decimal place. And there's our confidence interval. So now let me show you how to do this with a textbook. Here's the table A3 in the back of our Navidi textbook, and it is a table that helps us do computations with the student t-distribution. You can see here at the top we've got an alpha, so this is the alpha that goes along with our confidence level. And you see there's a few choices for the alpha value, but these are some of the more popular choices. So like an alpha value of 0.05, that would go along with a 90% confidence interval. Alpha value of 0.10, that would go along with an 80% confidence interval. So you get the idea. Limited number of choices here in the table. We don't have a limited number of choices to use in R. Over here in the first column, there's a nu, the Greek letter nu. It looks like a V. It represents the degree of freedom. So I can scroll down here and you can see it goes pretty high, and it even goes past 30. And if you look down here, you'll see a lot of these numbers, they don't change a whole lot. The last row, they've got a row here for infinity. These are the numbers that are that totally agree with the standard normal distribution. It's the idea that as n gets bigger and bigger, the student t-distribution gets closer and closer to the normal distribution. Well, there you go. That's that last row. So if you just need simple reference for some standard normal numbers for different alpha values, you can find it in the t-value table. So the numbers in the table represent what we see here in the picture. So the numbers in the table are t-values. And they're the t-values here. They're the percentiles at which the area above that cutoff is has probability alpha. Now this is different from the percentiles we've talked about. A percentile would be a number here at which the area below would be alpha. But in this case, the area below is 1 minus alpha. So you need to keep that in mind when you're doing these calculations using the textbook's t-value table. So for the example we've been looking for the 90% confidence interval. So our alpha value that we're looking for a single tail is 0.05. So that's this alpha value right here. And we've got 19 degrees of freedom. So let's go down, find row 19. There we go, 19. And the number we get here is 1.729. If you look back, and we'll look back in a second, at the calculations we did with R, it gave us a negative 1.729. That's because R is looking at percentiles, and it says the area over here, the place right here, negative 1.729, is the place where the area to the left is 0.05. What this table here is giving us is the number where the area to the right is 0.05. And by symmetry, those numbers are going to differ by a sign, plus or minus. So that's how you use this table. I'll repeat. Our alpha value for the problem we've been working is 0.05. Our degrees of freedom are 19. And so here this tells us that our t-distribution number is 1.729. we just saw from the textbook, the t value it tells us for 19 degrees of freedom and an alpha of 0.05 is 1.729. And its t-distribution, this number represents the number at which above it we have an area of 0.05. And because the t-distribution is symmetric, we know that it's at negative 1.729, that the area below that is 0.05. But this, either way, it turns out it doesn't matter if you put a positive 1.729 in here or a negative 1.729. The plus or minuses will fix it for you. So you can just go ahead and put that in for that, and everything will be groovy. And you'll get the same numbers, just get the same answers. And that's the whole point of looking at the textbook too. All right, I've done what I wanted to do. Hopefully this is interesting and useful to you. I'll see you next time.